Okay, we're going to talk about one more little thing here to do with derivatives before we kind of go on to the next main topic in the course. And so this topic is called differentials, and that word sounds really similar to differentiation. It does have to do with differentiation, but it is not exactly the same as a derivative. It is related. All right, so we're going to start by going back to the basic idea that we started with when we started with derivatives. And we started with the idea of slope of a secant line. So remembering that a secant line is a line between 2 points on a curve. So any 2 points here, and then we calculate the slope of that line. We've got m is change in y over change in x, or we might write f of b minus f of a over b minus a. Or when we started to talk about derivatives, we labeled one of those points as x and another point as x plus h. And so we had f of x plus h minus f of x all over x plus h minus x. So again, change in output over change in input, and then the x's cancel. And so that difference quotient there should look like what you remember thinking about as we calculated the slope of a tangent line. So we took that difference quotient that we had, and we took the limit as h approached 0 of f of x plus h minus f of x all over h. And provided that limit exists, we call that the derivative of the function at x, or we denoted that dy dx. And so we have these two similar notations, delta y over delta x. That's actual change in two distinct y coordinates divided by change in two distinct x coordinates. But that's very similar to this Leibniz notation dy dx. They're not the same thing, but when h is really small, provided that derivative exists, we should have that the slope of the secant line is very close to. So I'm going to use this approximately equal to, not equal to, but approximately equal to dy over dx. We can talk about, for the slope of the secant line, this delta y and delta x. Those are actual change in y and change in x. And so that's actually a division bar there. That's an actual fraction. On the right-hand side, that's not actually a division bar. It's not actually a fraction. What we actually mean by this on the right-hand side here is the derivative with respect to x of the function y equals f of x. So it's an operator, d dx of y, just like you might have cosine of y or square root of y, d dx of y. But with the idea of differentials, that allows us to think about how we might talk about the dx and the dy separately. Right. So sometimes students who don't quite understand the symbols they are writing down write things like dy over dx and think about that like a fraction, but remember that it is not. It is d dx of the function y, derivative with respect to x of the function y. All right, but differentials is how we are able to talk about dx and dy separately. So it is a whole definition, so I'm going to go ahead and write that down here. All right, so we're going to start first of all with some function, and we'll assume that that function is differentiable. And then we can define the differentials, two of them. Dx, we're going to treat as an independent variable. So when we think about function behavior, independent variable would be the input variable, or what the other function depends on. And so it can vary. Dx can take on different values. Dy is a dependent variable. It depends on something else, and it is defined as dy equals f prime of x dx. Okay, so dy is defined in terms of dx. So this is the definition of what dy represents. It is not the same as that I just multiplied both sides here by dx and they canceled on the left side. But you can also write this as dy equals, if I replace the f prime of x with the dy dx notation, I have this. And it looks sort of like these dx's should cancel, but they don't actually cancel because this dy over dx, remember that's not a fraction. That's not really dy over dx, it's d dx of y. So those don't really cancel. But this is called suggestive notation because it looks like they should cancel. So there are two ways that we will use these differentials. One of them, we will use dy by itself. And we will be working on that in Chapter 5, which we will be starting soon. And the other way that we will use that is as an approximation for an actual change in y. So we'll use the key idea that delta y over delta x is approximately equal to dy dx when the h is small. Okay, so that's how we're going to use that in this example here. So it actually asks us to find the differential dv, but we're going to use that as an approximation here. Okay, so in this example here, I do not have the variables x and y. I have different variables, in this case v and r. So if I'm going to calculate the dv, I have v as a function of r, then by definition we would have that dv is defined to be dv dr times dr. And again, the dr's don't cancel, but that notation is convenient because looking like they should cancel helps you know that you've got this set up correctly. All right, so let's calculate the derivative of v with respect to r. So I'm treating v as the output variable and r as the input variable. So I'm just going to differentiate that. And I can cancel these 3's here. So I have dv is 4 pi r squared dr. All right, so that's the first thing that it asked me to find, is to find the differential dv. And then the second thing that it asks me to do is use that to approximate the maximum error in volume if we've got this measurement on radius. All right, so I want to talk a little bit here about this measurement on the radius. So the idea here is that when you measure things, there's always measurement error that has to do with the precision of your measuring instrument. So this idea here would be that I've measured the radius to be 10 centimeters. But there is a measurement error, possibly because of the precision of my instrument, of plus or minus 0.5 centimeters. And so that plus or minus 0.05 centimeters is the change in r from what it really would be here. The idea here is that we want to use this dv that we have here to approximate the change in v, or the error in calculating volume. So the idea here is that what I have written down here are the actual differentials, but I can use them as approximations for the increments. So delta v is going to be approximately equal to dv dr, so 4 pi r squared times delta r. And this is using differentials to approximate increments or error. All right, so delta v is going to be approximately equal to 4 pi, my radius is 10, and my change in r is plus or minus 0.05. All right, so when I multiply that out, I'm going to get 400 pi times plus or minus 0.05 is 1/20th. You can use your calculator certainly, but I'm going to get plus or minus 20. All right, so I want to just label this here. That would be in cubic centimeters because that's volume. And I want to just emphasize a little bit here that this tiny little measurement error, 0.05 centimeters, that's a very, very small possible error in our measurement. But this possible change in volume is actually pretty big. Pi is a little bigger than 3, so this is a little bit bigger than 60 cubic centimeters. One of the important things here about using this is understanding the idea of error propagation. That when you have a small measurement error in one variable, when you use that to calculate other things, that you can end up with larger and larger measurement error in the future calculations there. All right, but the homework problems that you're going to do are all pretty similar here to 2. The basic idea that slope of tangent line is approximately equal to slope of secant line, and you're going to calculate a differential and then use it to calculate a possible error in some other variable.